It turns out that double slits are not the only um, option that we have to getting these strange results of wave features of light. One of the other possibilities is taking a disk. Now, if we have light from all directions, then things look sharp. When light's in all direction. Kind of fills in the gaps. But when light comes from a point source, well, you have light rays that are coming in, and then there's this point at which they will bend behind, in this case a disk, and it will put a little dot, little bright spot in the center of the shadow. And we can see that here in the drawing. Change my color. Here we see this little white spot in the center. It's not really big, but it's there. It's not a piece of dust. That's an actual white spot from these light waves interacting and creating constructive interference in the center of this shadow of this disk. Now, if we look at a edge, here we have a razor blade. You can see kind of these patterns inside, but if you look in really close, you can actually see these wave patterns occurring, even though this is a single slit. So we're still getting this wave nature in other ways than just the double slit experiment. So let's look at the single slit and see what we can come up with for describing that. So when the rays are directly through the slit, you get a very bright spot. Happens at theta equals 0 degrees. And this spot, this band is going to be very, very large. Now, because it's very large, it's going to end up taking and shifting our dark and bright spots from this point on. So here we have a case where at an angle, you have half a wavelength in the center and a wavelength at the top. Well, it's the center that we're kind of interested in, but it's this wavelength here that we'll have to deal with in the calculation. And so our dark spot happens when sine of theta is equal to lambda divided by d. D is just the distance of this slit. So it gives us a dark spot. And when I have 3 lambda over 2 pi, 3 lambda over 2d, well, here my wavelength is in the center, and I have these out of phase on the ends, and so I'm going to get a bright spot because I have the lambda here in the center, and the others are going to cancel themselves out, and I get a bright spot at 3 lambda divided by 2d. So the sine of theta equal to 3 lambda divided by 2d gives me a bright spot. And then for a dark spot, here again I'm going to have 2 lambda, but that just puts more of the interference, destructive interference in the mix, and so I get a dark spot at sine of theta equals 2 lambda divided by d. So the maximum is at theta equals 0 degrees, and because the central spread is so wide, it's going to offset our locations for minimums and maximums. So the maximums will occur when we have big D, size of the slit, times sine of theta is equal to m over 2 times lambda. And this is where m is equal to 0. We skip plus or minus 1 and we go directly to plus or minus 3, plus or minus 5, plus or minus 7, on. Now notice that we're missing plus or minus 1. And the minimums are going to occur at d times sine of theta is equal to m lambda, where m in this case is equal to plus or minus 1, plus or minus 2, plus or minus 3, and as we go. So now we can calculate and find the minimums and maximums based on a single slit, but just remember that the formulas for double slit are not the same for single slit. Don't get those messed up.